Alrighty guys, we're going to get rolling with our impulse notes by the one and only Mr. Weiss. First thing I want to talk about is impulse. And what is it? Well, we're going to say impulse is equal to the change in momentum. And in case you forget what change in momentum is, it's going to be abbreviated by a triangle, or we call that a delta. So it says delta P. And delta P again is just the change in momentum. And that really just means momentum final minus momentum initial. Impulse is going to be represented by the symbol J. So that is the symbol for impulse, not the units. Okay, that's important. And impulse is going to be a vector, meaning that it can be positive or negative, because we can have less momentum at the end than we have at the beginning, or more momentum at the end than we have at the beginning. Therefore, meaning it can be positive or negative. The units of impulse are going to be newtons times seconds. How do we calculate it? Well, let's talk about that. Impulse, which we are representing by the letter J, is equal to delta P, which just means that impulse is equal to the change in momentum. Just like I said before on the last page, that delta P equals change in momentum. And again, in case you didn't write it down on the last slide, momentum final minus momentum initial. Another way to calculate it is saying that impulse is equal to force times delta T. And force in this case is our net force, and delta T is the time period of that net force. And what we mean by that time period is the amount of time that the net force is acting over. And lastly, impulse is going to be the area under a curve of a force versus time graph. So if we look at these equations, we want to figure out, how does force change momentum? Well, net force will change an object's momentum over the time that it is exerted. Therefore, force is the rate at which momentum changes. And an example of that is just saying that the larger momentum change over a shorter time duration is going to result in a larger net force being applied. And on the flip side, a smaller momentum change over a longer time duration is going to result in a smaller net force applied. And we'll show what this looks like at the end in an example or two. But the gist of this is just that bigger momentum change over a smaller period of time means a huge net force. And we can see that in our equation. If we just look at this equation here, delta P is on top and delta T is on bottom. So the bigger the momentum and the smaller the time, the bigger the net force. So how do we find impulse from a force versus time graph? We mentioned that earlier in the notes, and I want to talk about it right now. First thing we need to note is that impulse is the area under the curve of a force versus time graph. So the area under the curve is referring from here down to the x-axis, and here down to the x-axis. And you guys did something similar to this in our energy unit when we figured out work and we were given a force versus displacement graph. So areas that are above the x-axis are going to be positive impulse. And remember, delta P is our change in momentum, but delta P also equals impulse. The area below the x-axis is going to be a negative impulse. What if we have non-constant force, which is kind of what we have in our problem here? The first few seconds, we have that constant force, a nice straight line, and then after that, we notice that our line becomes sloped and heads towards the x-axis. So this would be classified as a non-constant force. How are we going to figure that out? Well, we're going to have to divide the graph into sections and add up the impulse of each section. And this is something you guys did before, like I mentioned, with our energy and work unit when we figured out work from our force versus displacement graphs. So let's continue talking about this and let's show an example. So here's the graph from before, and now I'm going to split up those two sections. So as you can see, I have one section of area and another section of area because I had a non-constant force. I split one of them up, my red part, A1, into a rectangle, and the other one is into a triangle, A2. So after I divided up those sections, all I have to do is add them up now to get the total impulse. A1 is a square, just like I mentioned, so the area of a square is base times height, and A2 is a triangle, and the area of a triangle is half base times height. So here's an example, just like I talked about on the last page, of a negative impulse, how this is under the x-axis, and these are negative values here for force, so I should expect a negative impulse. And on the left side, these are above the x-axis, so I should expect a positive impulse. So let's quickly recap some important concepts. First one is our equation, and here I give you two equations in one, just saying that impulse is equal to the change in momentum, which is also equal to force times delta t. Again, delta p is equal to the change in momentum, F is our net force, and delta t is the time period of the net force. And that's just referring to the amount of time the net force is acting over. Impulse is the area under a curve of a force versus time graph, just like we talked about on the last slide. The area above the x-axis is going to be classified as positive impulse, and the area below the x-axis is negative impulse. And again, below the x-axis is the right side, so this graph over here, and above the x-axis is talking about this graph right here. Positive impulse is going to result in a net force that points in the positive direction. And a negative impulse is going to result in a net force that points in the negative direction. Let's take a look at an example here, one specifically that deals with math and our equations. There are two cars. Car A has airbags and car B does not. Both cars are traveling at 10 meters per second before the collision, and they come to a stop after the collision. Car A and car B have passengers that have a mass of 70 kilograms. Passenger A's collision is 0.01 seconds long due to the airbag, so the airbag has extended that time, it has made it longer. And passenger B's collision is 0.001 seconds because there are no airbags, meaning that that passenger just hit the windshield immediately. The airbag was not there to slow them down. Find the impulse of each of these situations. Okay, so in this problem, we can see some similarities here. Both cars are moving at 10 meters per second. Both cars come to a stop. Both cars have passengers with mass of 70 kilograms. And the only difference is the time in which this collision takes place. Passenger A, their collision is 0.01 seconds, and passenger B is 0.001 seconds. We also want to find out the force exerted on the passenger in each situation. So see if they have the same force exerted on them or if they will have different forces. So let's start by finding the impulse of each situation. And here's our equations that we need. So passenger A, their initial velocity was 10 meters per second. Their final velocity was 0 meters per second. Their mass was 70 kilograms. Their final momentum would be mass times velocity final, which is 70 times 0, which means that their final momentum is 0 kilograms times meters per second. Their initial momentum is mass times initial velocity, which is 70 times 10. That gives us an initial momentum of 700 kilograms times meters per second. Therefore, their impulse is equal to the change in momentum, which means momentum final minus momentum initial, which just tells us that their impulse should be negative 700 newtons times seconds. Let's take a look at passenger B now. Passenger B is moving with an initial velocity of 10 meters per second. Their final velocity is 0 meters per second. Their mass is 70 kilograms. Their final momentum is equal to mass times final velocity, which is 70 times 0, which means their final momentum is also 0 kilograms times meters per second. Their initial momentum is equal to their mass times their initial velocity, which is 70 times 10, which is also equal to 700 kilograms times meters per second. Therefore, their impulse is equal to the change in momentum, which is just negative 700 newtons times seconds. That means that they have the same impulse. And that makes sense because their momentums are the same. Their initial momentums depend on their initial velocities and their initial masses, and their final momentums depend on their final velocities and final masses. Therefore, impulse was the same. But now let's take a deeper look at this, and let's look at the force exerted on the passenger in each situation. And here's our equations again. So passenger A, they have the airbag, don't forget. Their impulse was negative 700 newtons times seconds. Their delta T, or the time of that collision, was 0.01 seconds. So if impulse is equal to force times delta T, and we manipulate this equation to solve for force, we find out that force is equal to impulse over delta T. So if we plug in our numbers, we end up with force is equal to 70,000 newtons. Let's say Mr. Weiss has a weight force of 700 newtons. That's equivalent to 100 Mr. Weisses standing on you. Let's take a look at passenger B now with no airbag. Passenger B has an impulse of negative 700 newtons times seconds. Their delta T was 0.001 seconds. And again, we know that impulse is equal to force times delta T. Manipulated to solve for force, we know that force is equal to impulse over delta T. If we solve this one, we find out that the force is equal to 700,000 newtons. Again, I have a weight force of 700 newtons. This is equivalent to 1,000 Mr. Weisses standing on you. 100 versus 1,000 Mr. Weisses is a huge difference. So what does that mean? That means that you need to make sure that your cars have airbags and that you're wearing your seatbelt. Because if they are wearing their seatbelt in addition to the airbags, their collision time would be even longer. And the longer the collision, the less force you are going to feel. That's why if you ever get in a car accident, it's actually a good thing that your car compresses onto itself. And the reason being is that when the car is compressing onto itself, it is making that collision time bigger. And that's the reason why cars aren't meant to withstand collisions. Because if your car is in very bad shape, it actually is a good thing because it means that your car is absorbing the impact, which means that it's keeping you safe because it's lowering the amount of force that you're going to feel. So all in all, make sure when you guys are driving, obviously be safe, wear that seatbelt, and make sure that you're driving a newer car that has airbags as well.